Okay, let us begin our seminar. And before the talk, I would like to give an announcement. At the end of May, Professor Uraltseva, my teacher and teacher of many of us and a friend of many of us, becomes 90. This is a non-trivial event, and we wish to organize a small online meeting dedicated to this event. Now, the registration is open at the site of Euler Mathematical Institute. Yeah, and I will also give a link to the seminar list. Yeah, please registrate all who wish. And now it's my pleasure to introduce our good friend, Professor José Francisco Rodrigues from Lisbon. And please, you can start.
Okay, thank you very much, Alexander. It's really it's a pleasure to be here on Zoom. It will be much better to be in person in St. Petersburg among you. But as you know, the times do not allow this to be done now. But I take this opportunity to talk on recent results that I got with my colleague Lisa Sanch, who is here with us in this cyberspace. And we wish to dedicate this work to Vslobod Alexievich Sonikov, that we miss very much. And you know already the abstract. The title is a little bit odd. Probably it's quasi-variational solutions to thick flows. So thick flows is something that probably some of you already heard me 10 years ago, because in the meeting in St. Petersburg, in Steklov in St. Petersburg, in 2013, in the birthday of the 80th birthday of Sonikov, I gave a talk in September, and this even maybe you can remember some of you this diagram. I just went to my old presentation because I want to continue this topic. And the topic, I think mathematics is quite interesting. I also have some novelties today, because it is also a good memory, that meeting in St. Petersburg, not only because it was celebrating the 80th birthday of our friend Sonikov, but also that I gave this talk, and I thought at that moment that was something really very, very new. And when I was in the airport, I just coming back, I just noticed an email that was a submission to Interface and Free Bounders. This was in September, 13th September 2013, a submission to the journal. At that time, I was the coordinator, Interface and Free Bounder, by Carlos dos Reis, about a very similar model. And they were taking, this is exactly this, then it was published. Of course, I did not review the paper. That was, of course, done by other editors. But I was a bit surprised by the coincidence. Then I discovered that they had already a preprint some time ago, but I did not know at all this work, which is only the steady state and some numerics and without convection, just the Stokes flow. And then I finished I complete my presentation with the first contribution that was published in Zapesky, and Then I was 10 years later, I come back here to dedicate this because I have some advance, as you can see. And I was trying to see what is about thick fluids. If you go to thick fluids in Google, today you see in medicine sites, lots of thick fluids as remedies for medicines. However, in literature, it is still in rheological papers, these thickness fluids is still a research topic. In mathematics, I know very little that has been done since the last days because the problem is certainly quite difficult from a numerical point of view. But from a mathematical point of view, it's quite interesting as I try to remember you and to show you that we can do something on this. So what are, in fact, the thick fluids? Just see this movie. This movie are people walking on a thick fluid. Maybe some of you remember this film. I presented 10 years ago. This is a thick fluid because with big tension, it behaves almost like a solid, as you can see. And of course, this is funny, just to give you an idea what is the thick fluid. But if you go without running it, so you see that if you run on it, so you go very fast, but if you go slowly, it is really a fluid. And the guy is going to show that it's really a fluid. You see? Okay, this is a nice motivation. So let's see from the rheological point, from continuum mechanics point of view, it is the viscosity, which depends on the flow and on the stress as discontinuities. And this can be recovered as a asymptotic model from this non-Newtonian law that goes back to 67 when Lazinskaya proposed this model for some power, which is a kind of Laplacian type for the rate, the stress rate of the stress displacement, the rate of displacement d, u is velocity, and the fact that when you take p going larger and larger in the limit, you get this constraint that in fact the d of u, the symmetric part of the gradient of the velocity, should be bounded by 1. And you see, this is the usual diagrams. We have Newtonian, the thick flows, and this is in a certain sense kind of a dual in the sense that the Bingham is the other case. So you take the stress, the shear rate that is bounded by 1, so you cannot go along 1, while in the Bingham is different. Okay, so in fact, what I presented more than 10 years ago was exactly, you take just this system, the non-Newtonian system, and you just take this SP, which is given by this Lazinskaya law, with possibly 2 different nonlinear laws. You can take, and you take just the P going to infinity. If you take Q equal to 2, you just have the usual Navier-Stokes. But it's Navier-Stokes provided you are below the threshold. You see, now you introduce this convex set and this notation, which is, of course, a classical subspace of the Sobolev space with the divergence free. Of course, we take the zero boundary condition to simplify. And in this, but this is a quite important constraint, which gives a lot of regularity, in particular the uniqueness. There is no problem regardless dimension. And of course, because it is even a constraint that is quite strong. And in fact, you can even take the existence theorem that I presented 10 years ago and is published in this paper in Zapersky. And in fact, it is a simple result. A simple result that has the advantage also that you can let the mu go to 0 and get a kind of Euler flow with this constraint, which is also quite interesting as a mathematical object, because as far as I'm aware, the uniqueness is not clear in that case. However, in the viscous case, it's clear that you have uniqueness of a strong solution. Why do I say it's a strong solution? Because the time derivative exists as an L2 function. But I am interested in more general problems. In fact, I start already on more general problems in the case where the threshold of the strain rate is a given function, and this is the variational inequality case, but it is a threshold that can depend on x and t, even if you like. Of course, it should be positive. And in fact, nowadays, what I try to understand is that this is a nice problem in the sense that it can be even extended to the case where this threshold can depend on the solution through some complicated functional way, because these thick flows in real life, they maybe change the behavior. For instance, with the change of the temperature, with the change of some chemical composition. And in fact, it's not clear that this threshold is just a priori given. Of course, one is this ideal case, is a priori function psi. We don't know exactly what is this psi. Of course, it depends very much on the rheology of each material, and probably lots of research must still be done in order to understand better this model. Nevertheless, from a mathematical point of view, we can play around and do all this mathematical theory and get interesting new results, in particular for the quasi-variational case. What means the quasi-variation? It means it's basically when this threshold psi depends on the solution itself through some functional way. I shall give two examples later on. And in fact, what means the constraint? The constraint means that you have a kind of Navier-Stokes flows. If you are below the threshold, this is just the equation, because this Lagrange multiplier, which will classify this parameter coming in viscosity as a Lagrange multiplier, is 0 if you are in this region, and is no negative, but is unknown if you are in the zone where the threshold is attained. And this is a little bit formal because we don't know exactly, I mean, you shall see in what sense this equation should be satisfied. In fact, even for strong solutions, you may have weak or strong solutions. Strong solution is when the time derivative of the velocity is an L2 function. But even in that case, what is the regularity of this Lagrange multiplier? This is, in fact, a quite interesting issue. And as you shall see today, with Lisa Sant, we have been working on this. She has been working also on that direction in different models, elliptic, parabolic. And now I even have some...
Excuse me. May I ask, the square bracket means simply that it is a function of u?
Yes, it's a functional. I mean, there is some implicit, I will give you some example. It could be an Emitsky operator in some cases, or through some compositions of some functions, you see, or could be just because u is the velocity that enters as in the convective term of the temperature equation, for each equation, for instance, you see? So in fact, this square bracket means that is a functional dependence on the solution, okay?
Okay.
Well, so the novelty here, one of the novelties here is today is generalized Lagrange multiplier, because this is, in fact, at this moment, the only thing that you will see in the theorem in a minute, that in fact, this Lagrange multiplier is in the dual space of the bounded functions, which is quite a strange space, not very convenient. Even I do not know if there is any good way to make numerical approximations of those objects, because as you know, the dual of the L infinity functions, they are associated with these finite additive measures, which are not, well, they are studied in mathematics, but from the numerical point of view, I do not know any way to do it. So this is a quite interesting issue for numerical analysts, if they are willing to test, to approximate this Lagrange multiplier, generalized Lagrange multiplier in some sense. Okay, so we may have strong solutions or weaker solutions, solutions that do not have time derivative of the velocity as a function. And this is the case where this Lagrange multiplier problem that corresponds to the strong solutions of the quasi-variational equality, if they do not have the time derivative, we have the weak formulations. We pass the time derivative to the test function, requiring that the test function, in fact, is derivative as a derivative in some dual space at least. And this is the space without derivatives. So I will introduce some notations later on. Here are my notations. So basically, you see the VP, of course, basically we're working with V2. It's this subspace of Sobolev with zero boundary conditions and divergence 0. And but we are interested also to the case where the P can be infinity, because in fact, even if because we shall need a test function that have the infinity, the gradient. Well, in fact, as we see here in these notations, we need to introduce the time derivative in the dual space, and this we have this continuity. So, and we have the strong solutions in this form. The strong solutions, in addition, they can define almost every t, because then this is L2 functions, and you can write this in this integral form. In fact, this extra term with the gradient of u is in fact here just for symmetry, because as you know, this times this basically is 0. So only with w enters. Okay, now what are the first results? Now I'm still recovering now the results that already obtained in 10 years ago, when we have the strong solutions. For the strong solutions, and this is the difference and the assumptions on the threshold. Well, the threshold will be always assumed to be bounded above and strictly positive below. So these are two important constants in our model. And this, if there is a time derivative in L infinity, this corresponds to the strong solutions case. And if for weak solutions, we relax and we have no time derivative on the threshold, but we have the continuity in time. So the initial condition, the initial condition is set once for all as belonging to the convex set as time 0, and the L2 function is once for all given as well. So the existence of unique solution of this problem is obtained by approximation, and this was already published 10 years ago. And there is some a priori estimates, because you see that we have a strong constraint on the D. So we have these a priori estimates on the D and on the solution itself. Do not depend on just on this parameter, not on the function itself, just on this given data. And also this continuous dependence result was obtained for these strong solutions as just usual procedure. The only interesting new novelty here is that we can include the continuous dependence with respect to the L infinity norm of the threshold psi. And in fact, you should note that here is power 2 and here is just power 1. So it's not Lipschitz, it's somehow older in these norms. And the constants are a little bit just numbered here, because you see they depend on the data. And we made in this work now make this constant explicit by one simple reason. When you want to go to the quasi-variational case, there is one interesting variant which has a contraction argument. So it's a fixed point by a Banach fixed point of contraction with respect to the variation of the threshold. And that's why these constants may be important to be given explicitly. And in this case, this is relatively simple for the strong solution first. And in a certain sense, this can be extended to the weak solution as well, because there are no dependence on the time derivative of the threshold, nor in the solution. And in fact, well, the proof, I just give here a few tricks, is more or less standard. The only delicate point is the right choice of the test functions, which must involve this parameter, which is constructed exactly by taking this variation of the thresholds. And because you see, when you take two different variation equalities, the convex are also different. So you cannot just take U2 in K1 and the U1 in K2. You just need to take this adjustment with that constant. And this is the feature. I mean, the important aspect is this parameter. And this will take a role in many proofs in this work. So the rest is more or less standard, this kind of estimates, finalizing with an estimate that is really ready for Grunwald inequality. So let's go now to go to the weak solution, weak variational inequalities. In fact, in the work that was finished about 4 years ago already with Lisa Santos and Fernando Miranda, a joint colleague from MINU, we had already as an application weak variation and quasi-variational inequalities of this type, but without this convective term. And this convective term has some difficulties for the weak solutions, and as I will show you in a minute. Well, for the existence is not a really big problem, because in fact the existence goes well because you know that solution is a priori bounded, so we can go without problem for the existence. But for the uniqueness, this is quite non-trivial, and this is exactly the difficulty that we had recent to see if we could work with unique weak solutions or not. And in fact, we can, because this weak formulation for this variation equality, which does not require any time derivative on psi, nor in the solution, is in fact unique. In this first theorem, we just give the existence, and the existence can be obtained using that a priori estimates which do not depend on time, and making a regularization of the threshold. Because having this convergence, if you go to this estimate, you see that we have a Cauchy sequence in this space, okay? And with this Cauchy sequence, we can construct a limit, a strong limit, and to get the existence is relatively simple. It's quite straightforward, I should say, because we have, by this approximation, a Cauchy sequence, and then, since this row tends to 1, the way it is constructed by exactly this approximation, psi to psi, because don't forget that when we have the approximated problem with the strong solutions, the convex also change. So we need to take that into account. And to go to the limit, we just mean the strong solutions are also weak solutions. So we go to the weak formulation, go to the limit with these estimates are simple. So the existence is not a big deal. And of course, this goes, these estimates, these continuous dependence estimates in the energy spaces, say, they also go to the limit for the weak solutions. But the point is, a priori, we get these solutions obtained by limit approximations. They are unique because of these estimates. But what we were able to prove recently, and this is basically due to, in fact, very strong perseverance of Lisa Sanch. She's listening to me, and we were discussing that we should try to go to prove the uniqueness, because you conjectured the uniqueness could be possible, but all the techniques, standard previous techniques, did not work with this quadratic term of the convection. Finally, she had a good idea to find the good test functions, and we were able to prove the uniqueness thanks to this kind of lemma that was already used by Lyons a long time ago, Jacques Lyons, when he was working on. But this lemma was previously only used in the case for strongly cursive problems, while in Navier-Stokes you have this convective term that presents some difficulties that finally, with some tricks, we could overcome. So this is the first new result is the uniqueness, and of course then also these weak solutions, they also have this continuous dependence estimate. Now let's go to see what we can do with Lagrange multipliers. Now, of course, concerning weak or strong solutions, we also have the strong version of the formulation, which is the one is starting here. And the strong version is written here in this sense. So this is the L2 function, basically. So the solution nu is in this H1, so it's a time derivative in L2, so this makes sense. And we introduce now this generalized Lagrange multiplier as an element in the dual space of bounded functions in the whole cylinder space-time. And this is why we introduce this notation for the duality, because we take test functions in V infinity. V infinity means that this dV is bounded. So this is in duality, because when we have also du, which is also bounded by the assumption on psi, we can write this in this form. In fact, we can put the duality, the vector duality. I mean, basically, this duality between L infinity and its dual, when you have vector, or we make the product with an L infinity function, you just use this definition, and this inner product here is, of course, an L infinity function. So this is in the dual of the L infinity scalar, and this, of course, is the dual in the vector. So the only difference is this is bold, and this is not bold if it's scalar. But this is a notation for this duality, is this in this sense that these generalized Lagrange multipliers are introduced. This is well, this is a new problem in a certain sense for these thick flows, even when psi is a priori given. And this corresponds, in fact, to the U, and this is the first theorem. I mean, with the standard assumptions for the strong solutions, which means that we require that the threshold psi is as time derivative bounded, then this is a solution in the strong sense, and the solution is a pair, and the component U, in fact, is the unique solution of the strong version of the variation equality. In general, we do not know about uniqueness of lambda, of course, because you see, when lambda, I mean, in the region where the region which regularity you do not know nothing about, when the du in modulus is equal to psi, the lambda is obtained in a very strange way by some limit, and is the very weak sense. So just to give you an idea about the proof of this theorem, and this was introduced for simple problems, elliptic problems, and then parabolic, and even hyperbolic problems. I recently have done something about the hyperbolic problem for this. For the hyperbolic problem corresponds, the scalar one corresponds to the vibrating membrane, which the gradient is bounded, which is a membrane that has a prescribed slope, cannot go beyond some prescribed slope. And this corresponds to some kind of elastic materials, but this is a different kind of problem. Okay, this means that basically what we do, and this is the standard way, is to make an approximation of the Lagrange multiplier by this nonlinear function, which can be chosen in several ways. One of the first example was exactly the power p, when we make this p going to infinity in the beginning. This was the first example, but it can be also done like, for instance, some kind of, so it's 0 for negative, and this can be some kind of exponential growth, and then you just cut in order just to have this bounded, in order to have no problem to solve the approximated, because this is a classical variational problem. And in fact, this k is basically monotone. So it is a monotone operator. So there is a unique solution in this space. And now all the issue are the a priori estimates as usual. And if you have the time derivative on the psi controlled, you can in fact put here the if you using Galerkin or some other technique for the approximated solution, you can test with time derivative, and then here it comes a time derivative here, which has controlled by the assumption. So in this case, you can have this estimate, and as well, these are already standard. But novelty here are the estimates that you can get on this additional regularization, and these are also estimates not very difficult to obtain, and they are basically, I forgot to put here the reference. I can give you a reference later on, but they are basically is in previous papers. So the idea here is that, okay, we need to apply this Alagoglu Banach theorem, but since L infinity is not reflexive, we just need to work with generalized sequence. But with generalized sequence, we have these limits in this in this sense. But in any case, we have can go to the limit, and with some tricks that were more or less developed for the scalar case, parabolic and elliptic case scalar, it goes here as well to this vectorial problem, and gives you that in fact the solution mu, this limit, satisfies these conditions in the duality sense. So this is in the dual sense, of course. Okay, basically now taking note that with those conditions we have these kind of inequalities. The solution of the limit problem, go to the limit, is not too difficult. The difficulty is to prove that in fact this limit is in fact in some sense equal to this lambda du, and this is the main part, but this was already solved in different cases. So basically with this inequality we get that the solution solves the strong formulation of variation equality, which, as you know, has unique solution. Okay, now with this tool we can go to the generalized problem. The generalized problem, it's similar. The only thing that we do not have at hand now is the estimate on the time derivative of the velocity. But then we need to have a weak formulation, taking the derivative for the test function and taking the initial condition here. So in a certain sense, we do not need to have the time derivative on psi. So psi just need to be bounded. But we shall require that psi is also continuous in time with values in L infinity, because you want to make the approximation from the, and in fact we have that property by the way we construct the solution. The way we can construct the solution, in fact, what you can say that by the same reason, the solution nu, so the solution has two components, the Lagrange multiplier and the solution, the velocity side, and the velocity is also a solution of the weak formulation of invariation equalities, which you know is unique. But on the other hand, this is in the duality sense, and the proof can be done in a similar way. Of course, using the approximation, and with this approximation, we can have also using generalized Cauchy subsequences that will converge to our solution. And the main trick here is to check that all the rest of the conditions, in particular these conditions, because this will converge to a big lambda, capital lambda, and to see that in fact it can be written in this form, and we have also these properties, is the tricks that are necessary to develop but I do not have much time to do it now. So let's now go to the new part for the quasi-variational problems. So in a certain sense, there is a continuous dependence, which can be quantitative in certain cases, for the problem with respect to the threshold. So when we make the threshold depend on the solution itself here, the way is, of course, trying to apply some kind of fixed point. And in fact, for that, we need to put some assumptions on this functional dependence, of course. And generally, there are more than one possibility, many possibilities, in fact. But in order to present just in simple cases, is just to see that, in fact, the image of this functional relation is always between these two values. It was part of our assumptions. In some cases, we can allow this go a little bit farther, but this is only in certain cases. And of course, we can start somewhere. In fact, since the solution itself has already some regularity, what we need is that we can, in fact, see by an example, that we can take in the domain psi quite large, then of course you can restrict. But in any case, if you want to apply the previous theory, variational theory, the image should always be in this class together with these two constraints. And in fact, with the previous assumptions, okay, this problem has a solution. Of course, now we don't know about uniqueness, of course, but it has a solution. And the solution is in this class. I mean, the Lagrange multiplier is in the dual level L infinity, and U is in the usual space, which has a finite D, bounded du. I mean, which is of course controlled by this because it is also bounded. Well, this first theorem basically, well, I think I forgot here something that is, yes, when I wrote this, I forgot to say that in a certain sense, we should have some kind of compactness here, which should be an assumption, but it's already satisfied in the next example. It should be written in 6.6 that we have a compactness of this functional relation. Otherwise, how can we get we could get a problem for the Schauder? Of course, we need compactness somewhere, and this comes hidden in this assumption and should be written here. I apologize, but read here this mapping psi, this functional relation should be compact. Let's give you an example. I give you an example because, of course, you can construct many more examples, but this example is also an homage to Solonikov, as I'm going to try to explain. And so here, basically, this is an Emitsky operator, okay? It's an Emitsky operator where zeta is, for instance, a temperature, is a function solution of a linear problem with convection. You see that the convection comes here. Of course, when convection comes here, we cannot just take V in L2. You need a little bit more than L2. But in fact, we can take the Schauder fixed point remember that the solution of our variation equality is bounded in L infinity. The solution itself, not the D, not the strain rate. The solution, the velocity itself, is always a priori bounded, depending only on those two constants and on this constant, basically on this constant. So taking that into account, what we have is that we can take V in L2, but with L infinity bound in some ball of radius M, for instance. So in this case, as you know, this linear system, and this is the Lazarskaya, Rautsev, Solonikov, And since Professor Altev is here, I think I'm not making any historical mistake claiming that this estimate is essentially in your book, of course, with Lenzinskaya and Solnikov. But as far as I remember, I was able to trace this estimate related to the same paper published by Solnikov in '64. If I'm wrong, please, Professor Altev, correct me. That's why I call this estimate, which is in your book, the Solnikov estimate. So it's my homage to Solnikov today, one more. And in this case, you see that for Q larger than D plus 2, this is compact. I mean, this inclusion is compact for the zeta and for the gradient. So the compactness of that psi operator comes here. And then we can take even this functional here, depending on the solution itself and its gradient. And just we need only continuity on this little psi, this function of these 4 variables. We just need these continuities on these variables. And of course, these constraints. And with this machinery, you can get this Schauder fixed point, which is enough to assure that we have existence of at least one solution for the quasi-variational inequality. So this is, I mean, this assumption on psi is a little bit motivated by this example. And this example has also some physical motivation because this threshold may depend on this zeta, and this zeta may just be a temperature, for instance, or a temperature or a chemical composition, something of this type that is ruled by some parabolic convective equation, linear or nonlinear. I mean, it could be more complicated, but this is for the moment enough to exemplify what we mean. Now, a second example, I mean, now we can have also the strong solutions. Well, for the strong solutions, we also construct some Schauder fixed points, but they're a little bit more delicate. Of course, in that strong solution, you need always to control the time derivative of the psi, of the threshold, which is a bit more delicate. But the strong solutions, they have a very simple example, at least for some control, smallness control on the data, because these a priori energy estimates very explicitly can give us the conditions to apply the contraction fixed point. I mean, this kind of, the old Banach fixed point theorem in L2 or in L2 it values in V2. For that purpose, of course, you need to make now some more restrictions on this functional relation. So here we had the idea, taking from other literatures, that if we split variable, I mean the functionality on U being a kind of a real number, and so not depending on x and t, and putting the dependence, splits dependent on x and t outside. In fact, in this case, we can put all the regularity on time derivative on this phi. On the other hand, this gamma, this functional gamma, for some Banach space, typically will be, in fact, Hilbert space in the L2, or the L2 it values the V2. The L2 it values in V2. In fact, it should be Lipschitz. Okay? But here now we can allow that, in fact, it should be, of course, strictly positive and strictly bounded. There's a misprint here. This, oh, no, this is not a misprint. This R star is a kind of possible dependence on the upper bound on L infinity norm of U. And so, but you see how we are going to do. We are going to basically what we are going is to use this Lipschitz property as a functional operator gamma with some Lipschitz constant that is here and should be, of course, controlled with respect to the data. And well, it's not very pleasant to control all this data. We see that we introduced these two constant A and B, which are given basically through this initial condition. The time could be not very large, also the F. And of course, this epsilon goes to control the L infinity bounded phi. And this R is going to be given, for instance, by this a priori estimate. You see that it can be depending basically on the given data. So, well, as you could expect, that if we control the constant in that continuous dependence of the energies to be sufficiently small, okay, as you expect, you have a contraction. And having contraction, you have even uniqueness of solution, okay? Existence of uniqueness of solution, which is a weak solution if we only require that this phi is not differentiable, just continuous. But in addition, if you take the phi Lipschitz with values in L infinity, so time derivative is also bounded, in that case, the solution is also a strong one. And of course, I mean, the uniqueness is for you because the solution of the Lagrange multiplier problem as a lambda, which a priori is not unique. And you can imagine that this is a lot of computations. We need to control all these constants, and we believe that this is basically okay. There are a second variation, which could give a different version of this operator psi, taking instead of L2, the V2. V2, remember, is L2 with values in L2. In V2 is this space with Sobolev space H1 of Cohomogam with divergence free. And basically here we have an example which is for this second theorem on contraction.
Excuse me.
Yes.
Here is some lambda 1 in the first large formula.
Yes. Oh, I forgot to mention. Yes, you are right. You are right. It is written somewhere, and I was very quick because I do not know how much time do I have. It is, wait a minute. It is, where is this up? It is a remark. It's here. Remark 2.3. Lambda 1, actually, you could guess, is the first eigenvalue, actually probably in omega. Okay?
It is the constant in the Poincaré inequality.
Exactly. Is this coming from here? Okay.
Okay. Thank you.
Okay. I thank your question because the remark was there, but I was too quick, and in fact the remark is here because in fact, if you want to control carefully and optimize all these constants, I mean the first eigenvalues, is important for that purpose. And this is why we try to be, this is a mathematical exercise, of course, to make all this composition of all these constants. And there is how this, well, there's a misprint also. This should be smaller than 1, probably. Of course, this should be smaller than 1. I apologize. I mean, this was written, it was corrected, and in the correction, strictly smaller than 1. I mean, of course, this is what we need for having this contraction. Okay. Well, this is a second example where you can, you can construct all these kind of examples, but the idea here was to have a strong unique solution, a quasi-variational unique solution, which is, of course, only in very special cases possible. But one possibility is to give a functional relation of the velocity with the threshold through a kind of integral operator. And this is a simple example where you can put the control on the time derivative on the kernel, on the variable of the kernel, okay? And here, here we need to use some kind of compactness in between because the time derivative plays its role for the compactness. And the fact that since the solution has a finite, is a bounded rate strain, it is in space is in all the continuous spaces. So we have kind of a possibility to apply a compactness theorem for the compactness of the psi. And basically, this is the example of the quasi-variational solutions that we are able to get at this moment. Of course, we could try to construct and to imagine other operators, but now, of course, we also need more physical motivations. And
it is something with memory.
In this case, yes. In this case, this example is an integral operator in time. Okay, but Alexander, don't ask me an example because I do not know enough rheology to give you an example.
Okay.
I mean, this is a mathematical example. I mean, if physically it makes any sense, I hope so, but I have no control because I have no even much information about the rheological literature, which of course does not go to these much general models. They go to very more precise experiments and try to understand how these complex fluids, they are quite complex, behave. Well, and I think it's time to finish and to thank your attention and to give my compliments to all of you and dedicate with Lisa Sanch this talk and these results to our good friend Solnikov that unfortunately is not anymore with us. Thank you for it.
Okay. Let's thank our speaker. And please, questions or comments? Okay, if not, please, Jose Francisco, switch off your sharing. Well,
no more comments.
Well, let's thank our speaker again.
Thank you. And send Alexander, send us the address of this conference. I don't know when which day it will be.
Yes. Okay.